All right, so the problem or the system covered in this video here will be a bit of a review here for um, our mechanics of materials. And what the system is a steel platform, which, as we'll see here in the first part, we'll assume is rigid, is supported by 3 posts in general, and they each have a cross-sectional area of 40,000 millimeters squared, so that's like 20 centimeters by 20 centimeters, and has a length of 2 meters. And prior to any loading, the middle post is actually shorter by 1 millimeter. So without any loading, it's actually only supported by um, the two outer beams, which I've labeled here as 1 and 3, and the middle one has a gap. So for assuming a rigid steel platform, meaning that we're assuming it's not bending, and we'll see that in part B, that it will check if it actually is rigid. But first for A, let's assume it's rigid and determine the normal stress in each of the posts if the load is 1,320 kilonewtons. So that's a huge load. But maybe this could be some sort of a statue of some kind or a monument. And so I think we've labeled everything except this A, and the A only comes in part B, and we'll come back to part B when we get there. All right, so the first step, this you can tell this will be an axially loaded system, but we'll always start with the free body diagram and the associated equilibrium ideas. Here's a free body diagram for the steel platform, and I've drawn F2 as dashed because we're not sure if that actually has a contribution or not. If we haven't closed the gap of S, or 1 millimeter, then F2 is just 0. There's no internal force, and there's no, therefore, applied force on the steel platform. So this is a free body diagram for the steel platform. So we have 2 cases here that we need to consider, and the first one, which is the easier one, we should just consider first. If the deformation in 1 and 2 is less than this S distance, less than 1 millimeter, then the sum of the forces in the y direction produces this. Just F1 and F3, the internal forces must balance the load P. Right? And so that's it. Well, we also know from symmetry that F1 and F3 must be the same, or they're the same material, they're the same geometrical dimensions, and everything's symmetric about the system. So therefore F1 and F3 are equal. However, you could also sum the moments about B, and we can see the sum of the moments about the B point here has no contributions from either the applied load or the force of the second bar, the second post, if we have closed the gap. So from that too, we know that F1 must equal F3. Okay, let's see here. So under that case, we'll just have, and then putting in that F1 equals F3, we have 2F1 equals, it must balance the applied load, and therefore F1, which also equals F3, is just half the load. Okay, so that's the easy result. If it's greater than S, then we have to put in F2, which we don't know in terms of, we can't use symmetry or anything about the system to know F2. So we just have 2F1 again, but now plus F2 equals P. And so if this is the scenario, this is a statically indeterminate system. Static equilibrium alone and the equilibrium ideas from our free body diagram doesn't alone solve for the unknown forces F1 and F2. So we'll move on to the plug in the force deformation relationships, because this requires us to then use geometric compatibility to get that additional equation to solve for the extra unknown. And here we just relate the deformation in each member to its force, its length, its cross-sectional area, and its elastic modulus, where 1 and 2 and 3 is living out here, but the equation for 3 from here on out will be all the same situation as we get for 1. So geometric compatibility, for the case again where delta 1 is less than or equal to S, that's the simple case from up here where it's a statically determinate system. We just get that our deformations are equal in 1 and 3, and the deformation in 2 is 0. So we just really need to calculate, this isn't a statically indeterminate system, but we would just need to calculate the deformation in 1, which I've done over here, kind of crammed it in. But here we have the deformation in 1 is that 1320 kilonewtons, the length is 2 meters. There's the factor of 2 there. 40,000 millimeters squared is the area, and 30 gigapascals is the elastic modulus. I've shown the unit conversions here. We need to convert the kilonewtons to newtons by a factor of 1,000. We need to convert this meter to millimeters by a factor of 1,000, right? So these are all being just multiplied by this equation, and I just kind of crammed it in here. And then we need to convert the gigapascals, which is in the denominator, to megapascals, because in this class it's convenient to use megapascals, newtons, and millimeters as our base units. With that, we get a deformation of 1.1 millimeters, which is bigger than the S gap. So this is not the right case. We have to go to the other case, the statically indeterminate system. And the statically indeterminate system, geometric compatibility now becomes extremely important and required to solve the problem. So this is the case we have, and so our deformation in 1 and 3 are both equal, which is equal to the deformation in 2 plus the gap. So the 2 doesn't start deforming until delta 1 has reached, the S gap, and then delta 2 starts deforming. So that's written in symbolic language here as delta 1 equals the gap plus delta 2. All right, so then we solve. So this is an equation once we plug in for what the forces are here. This is one equation with 2 unknowns, and then we have this equation, another equation with those same 2 unknowns. So here are our 2 equations. 2F1 plus F2 equals P, or we can rearrange this to solve for F2 in terms of F1. And our other equation is that, it's this equation where we've plugged in our force deformation relationships. So we have the deformation in 1 equals the deformation in 2 plus S. So a little bit of algebra now. That's that same equation where I've just plugged in F2 now equals P minus 2F1. Luckily, our lengths and our areas and our elastic moduluses are all the same. Technically, right, the length in 2 is a little bit shorter than the length in 1, but it's a very small change compared to its length, right? So 1 millimeter versus 2 meters, we can just use the same length, that they're both about 2 meters long. We see that the only unknown here is F1. Solve for F1. Get it by itself, and that's the algebra we have here. And this is the general relationship, and then we just plug in our numbers. And what I've used here is that PL over AE. We've already calculated PL over 2AE to be 1.1 millimeters, so a little bit of a shortcut. We've already done this calculation. We know that this factor is just 2 times as big, so 2.2 millimeters. And just plug everything in, we get that the force in member 1, which again is the same as the force in member 3, is 640 kilonewtons. We then go back to that relationship between F2 and F1. This comes out of equilibrium. Now we know F1, we just solve for F2 to be 40 kilonewtons. And this makes sense. This had better be a lot less than this one, because this one has been deforming a lot more. It's only that last extra 0.1 millimeters about where we're getting some stress, some internal force in 2, and therefore an associated stress. To find the stresses, we just then divide by the areas, which is 40,000 millimeters squared, to find that the stress in 1 and 3 is 16 megapascals, and the stress in 2 is 1 megapascals. Quick note here that if you look up the yield strength for concrete, it's on the order or about 20 to 40 megapascals. So this is of concern. If your factor of safety is 2, we're definitely over that. Even if your factor of safety is, closer to 1.5, you'd be concerned with this. But it's less than this range, so we'll say we're safe here. So now part B, going back to the problem statement, this asks, is our platform actually rigid? Is that a safe assumption? Well, let's assume that this is steel, so it has the elastic modulus of 200 gigapascals. It's not going to deform as easily as the concrete. The separation here between the 2 outer posts is 1 meter, and that the platform has the same cross-sectional area as the posts, 200 millimeters by 200 millimeters, and it's a square cross-section, therefore. So if that's the case, we go to our simply supported beam table, which I actually don't have with me right here, so you'll have to look it up yourself in the appendix in your book. We're just going to use a simply supported beam table with the load directly in the center. The maximum deflection therefore occurs at the center location where the load is applied, and it's just PL cubed over 48 EI, We know P is just 1320 kilonewtons. Our L is the length of our beam, which is 1 meter. Our elastic modulus is 200 gigapascals, and our moment of inertia for this 200 by 200 is just 1/12, bh cubed. But since b equals h, we can just do that that length to the 4th power. Plug all this in with the proper unit conversions, we get 1.031 millimeters due to beam bending. Remember, the original gap was 1 millimeter. So the beam bending itself is of the same order as the deformation in the concrete. So if we just had the beam deflection and we assume the concrete pillars were rigid, we would close that gap also. So assuming this is a rigid bar actually isn't that good of an approximation. As the load gets heavier and heavier, the beam is going to bend, and we're going to make contact with that middle post a lot sooner than what our original analysis showed. So what if instead we then had a platform that was really tall and skinny, right? So that's not really usable because we want to be able to put something on top of the platform. But if we did this, this would be a way to make that platform stronger by making the moment of inertia about that horizontal axis much bigger. So in this case, I have the same amount of material. It's still actually I've reduced our area by a factor of 2 here on accident. So let's say that this is actually 40. That would make this 40. We'll do this on the fly, and it's going to make our deflection. We're increasing I by a factor of 2, so it will decrease our deflection. Increase I, decrease our deflection by a factor of 2. So this is the actual answer here needs to be this divided by 4. The net result here, whether you use 20 by 1,000 or 40 by 1,000, we're going to be able to reduce our total deflection. So this is the answer you get if you do a 20 by 1,000. It's not really a fair comparison because we're using half the amount of material. But regardless, this is a much smaller beam deflection. Now, what about buckling? So if we go back to our original image, the system here, we see that we have compressive loads in all 3 posts once the load is applied. And so whenever we have compressive loading, we can ask about buckling questions. Is buckling going to occur? So we can, let's assume now that all the concrete posts are also 200 millimeters square cross sections. And we have the elastic modulus given. We can calculate our moment of inertia. Our effective length factor here is 2.0 because each one acts as a fixed free column. And the length here is 2 meters. With that, we can plug this in and find our critical load for buckling to be almost 2.5 thousand kilonewtons. And this is bigger than our F1, which was like 640 kilonewtons. So it's kind of by a lot. So buckling isn't going to occur here. Buckling, we need to have a much skinnier, much smaller cross-sectional area here for buckling to occur with this system and the way it's set up, and with the concrete. Another way we could get at this is to go to our critical stresses for buckling. And that's just a little bit different where we use the radius of gyration. Note here on the bottom, I have the KL over R, the whole quantity squared. Well, this is just R squared already. So the square I have here is just to the top part here in the denominator. And if you calculate this out, you get 61.7 megapascals, which again, compared to our stress in 1 and 3, this is 16 megapascals. So we're still safe here from buckling. And again, our concrete is going to yield at about 20 to 40 megapascals, so we're going to get yielding before we get buckling anyways. So that's what the main message is here. Yielding before buckling in our concrete posts. Okay.